At 6:58 a.m. on July 26, 1944, Technical Sergeant William Carter stood beneath the silver fuselage of a P-51B Mustang at Bodney Airfield in Norfolk, England. The morning air was cool, mist curling around the ground crews as they readied the fighters for another long-range escort mission deep into Germany. Carter wiped condensation from the engine cowling and glanced up at the pilot climbing into the cockpit. Inside the Merlin engine, coolant pumps hummed softly, the same system that had nearly cost dozens of pilots their lives only months before. The P-51 Mustang was fast, sleek, and revolutionary, but also dangerously unstable. Its liquid-cooled Rolls-Royce Merlin engine gave it unmatched range and altitude performance. Yet it came with a flaw so severe that early models were grounded after repeated in-flight failures. In climbs, coolant pressure spiked unpredictably. Radiator lines burst, engines overheated, and entire aircraft were lost to what engineers grimly called thermal runaway. Ground crews learned to fear the sight of green coolant spraying across the runway as pilots throttled up. The system that made the Mustang aerodynamic, a compact, streamlined belly scoop, was also trapping heat. The airflow through the radiator duct fluctuated violently, depending on speed and angle of attack. A few seconds of high boost or a sudden dive could send temperatures soaring past 270 degrees Fahrenheit. Reports from test flights in late 1943 described the same failure pattern. Power loss at altitude, followed by white smoke and engine seizure. At first, investigators blamed faulty pumps or poor coolant mixtures, but deeper analysis pointed to something more complex: the aerodynamics of the radiator itself. The laminar flow design that gave the Mustang its famous range created unstable airflow inside the duct, choking the system at high speeds. When the RAF's Air Fighting Development Unit ran trials at Boscombe Down, engineers recorded dangerous temperature surges just as the aircraft reached its optimal climb rate. The pressure inside the coolant system jumped by as much as 20 pounds per square inch in seconds, enough to rupture the radiator core. The Merlin engine could withstand enormous power loads, but not when the cooling loop lost balance. That was when one engineer at North American Aviation proposed a fix that his colleagues first dismissed as absurd: modify the internal ducting with a self-regulating shutter that reacted to air pressure, not pilot input. The idea was that the radiator's airflow could stabilize itself automatically at different speeds, equalizing temperature and preventing vapor lock. No one knew it yet, but that strange little mechanical tweak, a floating pressure door and a redesigned expansion tank, would turn the P-51 from an unreliable prototype into the most dominant fighter of the Second World War. The proposal came from an unassuming mechanical engineer named Edgar Schmude's assistant, a German-born designer who had once worked with Daimler-Benz on aircraft cooling systems before emigrating to the United States in the 1930s. His understanding of aerodynamics and thermodynamics was deep and unconventional. He argued that the P-51's radiator problem wasn't just thermal, but aerodynamic. Airflow, he said, was behaving like a living thing inside the duct, compressing, swirling, and stalling under certain pressures. His solution centered on a device no larger than a dinner plate, a variable position pressure flap inside the radiator scoop that adjusted automatically based on airspeed. At low speed, it stayed open, allowing maximum cooling. As velocity increased and ram pressure built up, the flap partially closed, forcing air through the radiator core at higher speed but lower turbulence. The result was a consistent pressure gradient that prevented boiling in the coolant lines. The concept drew immediate skepticism. North American's management worried the new flap would create drag, nullifying the P-51's aerodynamic advantage. Test pilots doubted a passive mechanism could react fast enough to save an engine at combat power. But Schmude approved a prototype test at Inglewood in November 1943. The modified radiator system, fitted to a P-51B-10 model, was shipped to Wright Field for evaluation under controlled conditions. Engineers ran a full power climb test from ground level to 30,000 feet. Normally, coolant temperatures would spike past 260 degrees Fahrenheit within minutes, forcing the pilot to throttle back. This time, the gauge barely reached 230 degrees Fahrenheit. The pressure stayed stable across the climb profile. The air coming out of the radiator scoop was measured at nearly 200 miles per hour, faster than the incoming airflow. The weird cooling hack, as one mechanic called it, had turned heat into thrust. It was the Meredith effect, a principle known since the 1930s but never fully mastered in combat aircraft. By precisely controlling how the air expanded as it exited the radiator duct, engineers could produce a small amount of jet-like propulsion, enough to offset much of the drag caused by the cooling system itself. In the Mustang, the new flap made the effect reliable and controllable. Flight data confirmed what the engineers suspected. At cruising power, the Mustang's radiator now contributed an equivalent of up to 150 pounds of forward thrust. The airflow remained stable at all speeds, and coolant boilovers, once common, disappeared entirely. Pilots no longer had to worry about losing their engine in a steep climb or dive. By January 1944, production lines at Inglewood and Dallas were quietly incorporating the new cooling system. Reports from the 354th Fighter Group, the first P-51 unit to enter combat in Europe, began filtering back. Pilots noted that their Mustangs ran cooler than before, even when escorting bombers at 25,000 feet for hours at a time. One flight leader described it simply, "The engine never quits. You can push it as hard as you like, and it just keeps running." What made the innovation remarkable wasn't just the added performance, it was how invisible it was. The modification involved no electronics, no pilot action, and almost no added weight. It was a mechanical self-regulator that exploited aerodynamic physics to solve a thermal problem. At a time when Allied engineers were still struggling with high-altitude engine failures in other liquid-cooled fighters, such as the Spitfire 9 and the P-40F, the Mustang's cooling system was suddenly the most reliable in the air. The shift transformed it from an experimental escort into a frontline weapon. Behind the scenes, Rolls-Royce engineers were astonished by the data. The new system meant the Merlin could maintain full rated power at 67 inches of manifold pressure without overheating. That gave the Mustang an effective combat ceiling above 40,000 feet, nearly 10,000 feet higher than most Luftwaffe fighters. In an era when air superiority was measured in altitude and endurance, this change alone altered the strategic balance of the air war. By February 1944, every major Mustang squadron in the 8th Air Force had converted to the upgraded design. The weird mechanical flap had become standard equipment, and the engine failures that once haunted the P-51 were nearly eliminated. Pilots stopped talking about coolant luck and started talking about Merlin reliability. The reputation of the Mustang as the most capable long-range escort in history began with that quiet, overlooked innovation buried deep in the aircraft's belly. A tiny piece of engineering genius that kept thousands of engines alive over Europe. By spring 1944, the Mustang's reliability over long-range missions had transformed the air war in Europe. For the first time, Allied bombers flying to Berlin could be escorted from English bases all the way to their targets and back. The new cooling system, combined with the Merlin engine's power curve, meant that the P-51 could climb faster, fly higher, and remain in combat longer than any fighter that came before it. But the true test of the weird cooling hack came not from laboratory measurements or test reports. It came from the sky over Germany. The 4th and 357th Fighter Groups were among the first to operate the improved Mustangs in continuous combat operations. In early March 1944, they joined the largest daylight raid yet attempted against the German capital. Hundreds of B-17 and B-24 bombers crossed into enemy territory, trailed by a protective ring of Mustangs. The air temperature at 25,000 feet was below minus 40 degrees Celsius, yet the P-51's radiators maintained steady thermal output. When Luftwaffe Bf-109G and FW-190A fighters dived from altitude, the Mustangs could meet them head-on without fear of their engines boiling over during the long climbs. Combat analysis from the 8th Air Force noted that earlier escort fighters, P-38s and P-47s, often had to disengage due to overheating or fuel constraints. The P-51 did not. Its cooling system automatically adjusted as pilots varied throttle settings, keeping the engine in a narrow optimal range that balanced temperature, pressure, and fuel consumption. Every flight engineer reading the after-action reports could see the difference. Coolant losses were down by 90%, mission completions up by nearly the same margin. Engineers back at Inglewood realized something extraordinary had occurred. A solution initially designed to prevent overheating was now directly improving combat performance. Stable coolant temperature meant stable oil viscosity, better cylinder lubrication, and consistent power output from the Merlin's supercharged V12. The engine could sustain full combat boost for longer periods, making the Mustang faster in prolonged climbs and more agile in dives. The effect on pilot confidence was equally significant. Before the modification, every high-power maneuver carried a small but constant fear that the red temperature needle would suddenly spike and the coolant would vent through the relief valve, marking the beginning of an engine seizure. Now pilots reported flying for hours without seeing the needle move. The P-51 was not just a machine, it was a promise of survival. German intelligence units quickly took notice. Captured reports from Luftwaffe analysis groups in the summer of 1944 described the P-51 as mechanically stable and resistant to temperature failure. Even under high load conditions, technicians inspecting downed Mustangs were puzzled by the small internal shutter hidden inside the radiator duct. To them, it appeared like an ordinary airflow baffle, not realizing its function as a self-regulating pressure device. Some Luftwaffe engineers assumed the Allies were using a new type of coolant or fuel additive. They never suspected that a simple mechanical linkage had neutralized one of aviation's most persistent design challenges. The improvement also gave the Mustang an aerodynamic advantage few noticed at first. With airflow through the radiator stabilized, drag was reduced across multiple speed regimes. In high-speed dives, where turbulence once caused instability in pitch and yaw, the Mustang now tracked straighter and faster. This gave pilots an edge when disengaging from combat or chasing German fighters trying to escape. By June 1944, as Allied forces prepared for the Normandy landings, the upgraded P-51B and the new P-51D, equipped with the same cooling system, dominated the skies over Western Europe. Their long-range endurance allowed them to patrol ahead of bomber formations, hunt enemy interceptors before they reached the target zone, and still have enough fuel to strafe airfields on the return flight. What made the story of this modification remarkable was how unremarkable it seemed at first. To most of the pilots and mechanics, it was just another part number, one more maintenance line in the technical manual. Yet its impact rippled across the entire European air campaign. Fewer lost engines meant fewer aborted missions, more bombers reaching their targets, and fewer pilots falling into enemy hands. As one after-action report from the 8th Air Force Engineering Section summarized in August 1944, radiator system now self-stabilizing, no pilot control required, engine performance sustained, failure rate negligible. The P-51's transformation was complete. The aircraft that once overheated on the runway now roamed above the clouds of Europe, its cooling system humming quietly beneath the fuselage, a mechanical miracle born from a single, strange idea. By mid-1944, the Mustang's transformation had reached the point where its weaknesses had become its strengths. The same narrow fuselage and tightly packed cooling ductwork that had once threatened to destroy the aircraft's engine now defined its superiority. The engineers at North American Aviation, working alongside Rolls-Royce, had done more than fix a flaw. They had created a closed-loop thermal system that functioned like a self-tuning engine, constantly seeking equilibrium. At Bodney, Leiston, and Debden airfields, ground crews noticed the change almost immediately. Maintenance hours per aircraft dropped sharply. Where the earlier Mustangs required radiator replacements after a few missions, the new versions could fly dozens before showing signs of stress. Coolant leaks, once common enough to leave green stains on the tarmac, disappeared almost entirely. The new radiator flap system automatically bled excess pressure and maintained a constant flow rate regardless of altitude or engine boost. Pilots wrote home about it without understanding the engineering behind it. Letters preserved in squadron records describe the Mustang's engine as impossible to kill, a machine that forgives your mistakes. To a combat pilot over Germany, that meant everything. They could throttle up through cloud cover, pursue a target, or climb to meet a formation of Bf-109s without the constant anxiety of watching temperature gauges rise toward the red zone. In technical reports, engineers began referring to the system as thermodynamic self-balancing. In practice, this meant that at any airspeed above 250 miles per hour, The radiator and the pressure flap created a steady-state airflow that absorbed and expelled heat with near-perfect efficiency. When the pilot reduced power, the flap opened wider, restoring flow. When power increased, the flap narrowed the duct, increasing pressure but reducing turbulence. The result was a stable temperature curve, regardless of maneuvering or throttle changes. This innovation also interacted perfectly with the Merlin engine's supercharger stages. As the engine compressed incoming air at high altitudes, the temperature of that air rose dramatically. In most liquid-cooled engines, this caused heat spikes that required throttling down. In the Mustang, the improved radiator system absorbed the excess without penalty, allowing the Merlin to maintain full manifold pressure far longer. It was an invisible partnership between aerodynamics and thermodynamics, the airflow around the aircraft sustaining the heart of its engine. Luftwaffe intelligence officers studying the wrecks of downed P-51s were astonished at how little damage appeared in the cooling systems. Radiators that had been hit by small arms fire often held pressure long enough for the pilot to return to base. The efficiency of the cooling loop meant that even partial system failure rarely caused instant engine seizure. German analysts concluded that enemy fighter engines show exceptional tolerance to heat and structural damage. Meanwhile, Allied engineers in England and the United States continued to refine the modification. Flight testing confirmed that the Meredith effect, the phenomenon of thrust generated by expanding hot air from the radiator, was not just theoretical. At cruise speeds near 350 miles per hour, the effect produced enough forward thrust to offset up to 90% of the radiator's aerodynamic drag. In effect, the P-51's cooling system was helping to propel it. This meant that the aircraft's range and efficiency were even greater than originally calculated. The combination of efficient cooling, reliable power, and long range gave the Allies a decisive advantage. With the introduction of the P-51D in mid-1944, the Mustang could escort bombers from English bases to Berlin, Leipzig, and even deep into Poland. It could fight for hours at high altitude without mechanical failure. The Luftwaffe, already stretched thin, could no longer contest the skies effectively. Every detail of the Mustang's success, from its engine to its range to its stability, traced back to that one weird engineering fix. The small automatic shutter buried inside the belly of the aircraft had changed everything. One report from the Air Technical Intelligence Unit, dated September 1944, stated plainly, the P-51 cooling system achieves self-compensating temperature control through aerodynamic management of pressure differentials. System failure rate statistically insignificant. Operational reliability exceeds all prior Allied fighters. What began as a desperate attempt to stop engines from exploding had become one of the most elegant examples of engineering efficiency in aviation history. The P-51 no longer fought against its own design. It used physics itself as an ally. As 1944 turned into 1945, the P-51 Mustang's evolution into the dominant Allied fighter was complete. But few outside the engineering community understood that its supremacy depended on something as humble as airflow and heat. Historians would later describe the Mustang as the fighter that won the air war. But at the time, pilots and strategists alike were still uncovering what made it so uniquely effective. The key lay not only in its range or firepower, but in its reliability under extreme conditions. By this stage of the war, the Luftwaffe's defensive network was collapsing, but the skies over Germany were still deadly. Long-range bomber raids to Berlin, Dresden, and the Ruhr pushed aircraft and pilots to their limits. At those altitudes, the cold could freeze lubricants and crack fuel lines. Yet the Mustang's engine temperatures remained stable. Reports from the 357th and 352nd Fighter Groups told a consistent story. During high-altitude escort operations, Mustangs could run at military power for nearly an hour without coolant or oil temperature exceeding design limits. That endurance was critical because escort missions often required fighters to fly at maximum climb power while weaving above bomber formations, scanning for enemy interceptors. Other Allied aircraft, and particularly the P-38 Lightning, struggled under those same conditions, sometimes suffering engine shutdowns when coolant froze or fuel vaporized. The P-51, by contrast, thrived in the thin air. The improved radiator system ensured that heat generated by the Merlin's twin-stage supercharger was dissipated efficiently, even in near-Arctic temperatures. The automatic pressure flap kept coolant circulation smooth, preventing the formation of vapor bubbles that could lead to cavitation and pump failure. It was this combination of aerodynamic control and thermal precision that allowed the Mustang to do what no other fighter could: fly 1,500 miles, fight at 30,000 feet, and return home without mechanical incident. Engineers at Rolls-Royce and North American realized they had achieved something unprecedented: a fully integrated power plant system where engine, duct, and airframe worked as one. The cooling system wasn't a passive component, it was an active participant in the aircraft's performance. In post-war testing, it was found that at speeds above 350 miles per hour, the heat energy expelled by the radiator produced up to 300 pounds of forward thrust, roughly equal to the drag produced by the entire cooling assembly. The Mustang quite literally powered itself through the air using its own waste heat. This was no accident. The physics behind it had been hinted at years earlier by British engineer Frederick Meredith, who theorized that properly shaped radiator ducts could convert heat energy into thrust. But before the P-51, no combat aircraft had successfully applied that principle in a reliable, controllable way. The Mustang's engineers had made it work not through advanced materials or electronics, but through geometry, pressure, and timing, a triumph of intuition and discipline. Pilots noticed the results in the most practical way possible. The aircraft simply performed better the faster it flew. In pursuit dives, where other planes gained drag from their cooling scoops, the P-51 seemed to slice through the air with growing efficiency. German pilots would later report that Mustangs accelerated unnaturally fast when diving, a direct byproduct of the thrust generated by the radiator's pressure system. The implications went far beyond combat. The success of the Mustang's cooling design influenced nearly every post-war aircraft to follow. The jet age was approaching, but the principles that governed the P-51's performance, airflow management, heat utilization, and pressure recovery, became cornerstones of jet engine inlet and exhaust design. The Meredith effect, once a theoretical curiosity, became a standard part of aerodynamic engineering education. Back in 1944, though, none of this was theoretical. It was survival. Every bomber that made it home over the Ruhr or Berlin owed its safety to fighters that could stay in the sky longer than their enemies expected. And every P-51 that finished a 6-hour mission without engine failure proved the value of a single strange idea: a self-regulating flap that turned a liability into an advantage. In the war's final months, the Mustang became the hammer that broke the Luftwaffe's will. German fuel shortages, inexperienced pilots, and relentless Allied pressure had already crippled their air defense. But what finished the job was the simple fact that the P-51 could stay in the air when nothing else could. The weird cooling hack that began as a technical fix had, by the spring of 1945, become a strategic weapon. In early 1945, as the Allies advanced deep into Germany, the Mustang's reputation was fully cemented. Luftwaffe pilots feared its silhouette even before contact. Ground troops learned to recognize the shriek of its diving engine as a sign to take cover. But behind the Mustang's domination was not just brute force or superior tactics. It was engineering precision that kept the aircraft performing flawlessly across thousands of sorties. The Mustang's improved cooling system had by then evolved into its final wartime form, combining mechanical reliability with aerodynamic finesse. Wartime maintenance records from the 8th Air Force show that coolant system-related failures had dropped to less than 1 per 1,000 flight hours, an unheard-of statistic for a combat aircraft operating under such conditions. The modification, once dismissed as experimental, had become a defining standard. At high altitude, where thinner air made heat transfer far more difficult, the system proved its worth repeatedly. During the February 1945 bombing campaign against Berlin, multiple squadrons reported engine temperatures that never exceeded the safe range, even during prolonged combat at full power. The pressure flap automatically compensated for reduced air density, adjusting airflow through the radiator duct to maintain steady coolant velocity. In engineering terms, the P-51 had become a self-regulating machine, a dynamic equilibrium of air and heat. The system's elegance was that it demanded nothing from the pilot. There were no extra levers, no adjustments mid-flight. The mechanism operated purely through the interaction of airflow and pressure, translating raw physics into survival. A pilot could focus entirely on flying and fighting, knowing the aircraft's internal systems were handling themselves. This reliability allowed P-51 units to execute new tactical doctrines. Instead of flying close to bomber formations as static escorts, Mustangs began to range ahead, hunting German fighters before they could attack. These so-called fighter sweeps were possible only because the Mustangs could afford the long periods of high power required to intercept and pursue at altitude. Without overheating or loss of performance, they could climb, dive, and fight across multiple engagements during a single mission. The Luftwaffe, meanwhile, was trapped by the limits of its own machinery. The FW-190A struggled above 25,000 feet, where its air-cooled radial engine lost efficiency. The Bf-109G's liquid-cooled Daimler-Benz engine performed better at altitude, but lacked the same cooling stability, forcing pilots to throttle back in extended climbs. Against the Mustangs, whose engines thrived in those same conditions, the German fighters were at a fatal disadvantage. Technical reports from the Luftwaffe's Forschungsanstalt für Luftfahrt, Research Institute for Aviation, confirmed that German engineers were aware of the Mustang's superior thermal efficiency by late 1944. Captured aircraft examined after forced landings showed that the Mustang's radiator outlet design, especially the internal pressure door, provided what one German engineer described as a nearly perfect example of Meredith thrust application. By then, however, the Reich's industrial system was collapsing. There were no resources left to redesign or test equivalent systems. The Mustang's engineers didn't stop refining the concept. Field modifications led to incremental improvements in airflow control and duct sealing. Each small change, a smoother hinge, a lighter flap, a tighter seal, added a fraction of efficiency. By the time the P-51D reached full production, the cooling system's performance curve was so stable that the U.S. Army Air Forces officially removed coolant overheat warnings from the operational checklist. In post-war evaluations, data from hundreds of flight logs revealed that the P-51's average engine operating temperature varied by less than 5 degrees Celsius across an entire mission profile. In an environment where thermal variation could mean the difference between life and death, that level of consistency was unprecedented. The effect on pilot morale was profound. Before, they had flown machines that demanded constant monitoring, where a few seconds of neglect could destroy an engine. Now they flew an aircraft that felt alive in a different way. Not temperamental, but self-correcting, almost intelligent. For many, this changed how they fought. They climbed higher, stayed longer, and pressed harder into enemy territory. Missions that had once been limited by mechanical endurance were now dictated only by fuel. The weird little pressure flap, born of a desperate fix to stop engines from exploding, had reshaped the boundaries of aerial warfare. By March 1945, the P-51 Mustang had become the defining image of Allied air power. Its performance, endurance, and sheer reliability made it the spearhead of the U.S. Army Air Force's daylight bombing campaign and the symbol of technical supremacy. But the transformation of the Mustang from a promising prototype into the ultimate long-range escort was not only a victory of design, it was a lesson in how small engineering insights could rewrite the rules of modern warfare. In the weeks leading up to the collapse of the Reich, P-51 groups operated deep inside enemy territory on a scale that had been unthinkable a year earlier. Some missions lasted more than 7 hours, covering over 1,500 miles. These flights demanded flawless mechanical endurance. Pilots often pushed their engines through cycles of full throttle and steep dives, then throttled back for fuel efficiency, repeating this process dozens of times per mission. Any instability in temperature or coolant flow could have been fatal, but the improved system held steady, flight after flight. One after-action engineering report from the 339th Fighter Group summarized the results of over 2,000 sorties. No engine loss attributed to cooling system malfunction, coolant pressure constant, performance unaffected by repeated altitude changes. It was an astonishing statement. a reflection of precision manufacturing and aerodynamic understanding, rare even by modern standards. At a fundamental level, the Mustang's cooling system had solved one of aviation's oldest problems: how to manage heat without wasting energy. The solution, born of necessity, was elegantly simple: use the aircraft's own motion to maintain thermal stability. Every molecule of air that entered the Mustang's radiator scoop performed dual roles. First, absorbing heat from the engine coolant. Second, accelerating as it expanded through the duct and producing forward thrust. Instead of robbing the aircraft of power, cooling now contributed to its speed. This made the Mustang unique among propeller-driven aircraft. Where most fighters suffered a measurable loss in efficiency at higher speeds due to drag from open cooling flaps or large radiators, the P-51's aerodynamic balance improved. It was, in essence, a machine that grew more efficient the faster it flew. The faster the airflow, the better the cooling. The better the cooling, the greater the engine's power output. The loop fed itself. Engineers later quantified the relationship in a series of wind tunnel tests at Wright Field in late 1944. They found that, at 375 miles per hour, the radiator outlet actually produced a small but measurable net thrust, the equivalent of 150 to 200 pounds. It was not enough to transform the Mustang into a jet, but it effectively canceled most of the cooling drag, a feat unmatched by any other piston-engine aircraft of the war. This aerodynamic self-sufficiency was especially vital during high-speed escort and interception missions, where fuel economy determined how long a squadron could remain over target. The Mustang's exceptional range, sometimes exceeding 1,800 miles with drop tanks, owed as much to its efficient cooling design as to its fuel capacity. A cooler, more stable engine required less enrichment and wasted less energy. The P-51's ability to maintain full power without overheating gave it the endurance to follow bombers across half of Europe and still fight on the way home. By contrast, Luftwaffe pilots found themselves constrained by the physical limits of their aircraft. The Bf-109's Daimler-Benz engine required constant manual adjustment of radiator flaps to prevent overheating or overcooling. In combat, that meant one more distraction for the pilot and one more chance for error. In the Mustang, all of it happened automatically. Pilots could devote their full attention to flying, aiming, and surviving. Their aircraft handled the rest. That invisible advantage translated directly into combat results. The P-51's kill ratio against German fighters exceeded 11-1 by early 1945. While tactics, training, and numbers all played a role, engineers quietly pointed to the data. Lower failure rates, higher sustained power output, and negligible temperature deviation. The cooling system, that small, unseen innovation, had given Allied pilots the confidence to fight harder and longer than their opponents. Even as the Allies prepared for victory, the Mustang's engineers continued gathering data. They recorded coolant flow rates, heat differentials, and aerodynamic pressure readings from combat-damaged aircraft. Every surviving plane became a flying laboratory, feeding knowledge into what would become the foundation of post-war jet design. As the final months of the war unfolded, the P-51 Mustang's dominance seemed absolute. The Luftwaffe was disintegrating. Its veteran pilots were gone, its fuel depots bombed, its aircraft grounded by shortages or destroyed on the runway. Yet even as the Allies achieved air supremacy, engineers at North American Aviation and Rolls-Royce continued to dissect the Mustang's every feature, determined to understand precisely why it had succeeded where others failed. They discovered that the cooling system's success was not just a matter of airflow or thermodynamics, it was also one of structural harmony. Every part of the Mustang's fuselage contributed to the regulation of heat. The aircraft's long, slender body acted as a thermal stabilizer, allowing heat absorbed in the engine compartment to dissipate gradually along the skin. The radiator duct under the fuselage, positioned at the center of gravity, ensured that the plane's aerodynamic balance remained constant even as coolant temperatures fluctuated. In effect, the Mustang wasn't just cooled by air, it was cooled by its entire shape. At Wright Field, post-mission inspections showed that temperature gradients across the aircraft's surface were more uniform than in any other fighter. Engineers noted that the fuselage stayed between 100 and 120 degrees Fahrenheit, during high-power operation, warm but never dangerously hot. The even distribution of heat reduced structural stress on the engine mounts and airframe, giving the P-51 a longer mechanical lifespan. This also meant that maintenance crews could push the aircraft harder without fear of warping or cracking under thermal fatigue. Pilots flying the late-model P-51D reported that engine management had become almost effortless. Where earlier fighters required constant monitoring of coolant temperatures, manifold pressure, and oil levels, the Mustang's indicators rarely moved. One squadron engineer wrote in his logbook, "No pilot attention required. Engine temperature remained stable across all phases of flight." That statement, while brief, captured the culmination of years of design refinement. The system's simplicity also made it remarkably durable in combat. Many Mustangs returned to base with bullet holes through their radiator scoop or coolant lines, yet their engines continued to run. Tests revealed why. The self-regulating pressure flap prevented sudden coolant loss by adjusting airflow when damage disrupted circulation. It bought pilots precious minutes to reach home before the engine failed. For a system that had started as a vulnerability, it had become a safeguard. In early 1945, captured German engineers began analyzing the Mustang's recovered wrecks and filing reports for the Luftwaffe's Technical Bureau. One document, later found in archives near Oberammergau, noted, "The enemy fighter exhibits a radiator configuration that converts exhaust heat into thrust energy. A precise balance of pressure and temperature is achieved through automatic control surfaces. It is both efficient and elegant." It was a professional admission of defeat, respect for a design that German aircraft, for all their innovation, never matched. The strategic implications of this innovation extended far beyond individual dogfights. The Mustang's ability to sustain maximum power for long durations made high-altitude escort viable, ensuring that Allied bombers could operate deep within German airspace without unacceptable losses. Between January and April 1945, American bomber losses dropped by nearly 70%, a decline that directly correlated with full P-51 deployment. The cooling system, though invisible in combat reports, had played a role in that transformation. By maintaining consistent engine performance, the Mustang also enabled new operational tactics. With stable temperatures at any throttle setting, pilots could use aggressive power management, short bursts of full power, followed by rapid descents, without mechanical penalty. This flexibility made the P-51 an agile predator. Luftwaffe pilots described their frustration in post-war interviews. "You could not make them break off. Their engines never overheated, even in long climbs. They would follow you until your fuel or nerve ran out." Even as victory drew near, the Mustang's engineers continued experimenting. They tested additional duct configurations, alternate radiator geometries, and variable inlet designs. Some of these refinements would later influence early jet fighters, especially in how intake geometry was optimized for both drag reduction and thermal management. The lessons learned from the P-51's radiator system became part of the foundation of modern aerospace design. Use heat, don't fight it. The principle that saved engines from exploding in 1943 would later guide engineers designing supersonic aircraft, machines that relied on controlled airflow and heat recovery to survive at high speeds. By April 1945, the war in Europe was effectively over, though the mission still continued. The P-51 Mustangs roamed the skies with impunity, their engines roaring above a defeated Germany. The Luftwaffe was a shadow of what it once was. Allied bombers flew over smoldering cities almost unopposed. For the pilots, the end was near. But for the engineers behind the Mustang, the work of understanding what they had created was only beginning. Post-mission reports poured into Wright Field and North American's Inglewood plant, each one reinforcing the same truth. Not a single engine failure had been attributed to overheating in months of continuous operations. The numbers were staggering. Tens of thousands of combat hours logged, thousands of sorties flown, and virtually no systemic cooling failures. Wartime data analysts, accustomed to charts filled with red warning zones and maintenance alerts, stared at flat, steady lines. Temperature variation across flights was minimal. Reliability was near absolute. For the first time in modern aviation, a fighter's cooling system was not a limiting factor. It was an enabling one. Every other major aircraft of the war had been constrained by temperature. The Spitfire's Merlin engines required careful throttle management. The FW-190's radial engine overheated quickly at altitude. Even the P-47 Thunderbolt, famous for its ruggedness, struggled with temperature fluctuations during extended climbs. The P-51, however, operated like a closed system, perfectly balanced between air, heat, and motion. This consistency translated directly into combat dominance. With each mission, the Mustang proved that sustained engine power was the most valuable asset a pilot could have. The ability to hold full boost for minutes instead of seconds meant the difference between catching an opponent and losing him in a climb. German pilots noticed this in every encounter. As one captured Luftwaffe officer later remarked, "The Mustang could follow us forever. We climbed until our engines groaned, and they were still behind us, calm and steady." At the engineering level, the cooling system's success stemmed from how seamlessly it integrated with the Merlin's thermodynamic cycle. The automatic flap adjusted air pressure so precisely that it kept coolant density stable across all altitudes. The result was a nearly constant rate of heat transfer, something that even laboratory engines struggled to achieve under controlled conditions. Every mission flown by a P-51 was a live demonstration of applied physics working at its peak. This performance also altered strategic doctrine. The U.S. Army Air Forces began planning escort missions based on the Mustang's reliability, extending operational ranges and duration. Squadrons were ordered to fly deeper into German territory, loiter over target zones, and remain overhead during bomber withdrawals, tasks previously deemed impossible. The confidence in the aircraft's mechanical resilience reshaped Allied air strategy. By the spring of 1945, the air war was no longer a contest of endurance or distance. It was a demonstration of dominance. In the background, engineers began to realize that the Mustang's cooling innovation was more than a wartime advantage. It was a glimpse of aviation's future. The idea that an aircraft could recycle its own waste heat to gain thrust was not limited to propeller planes. The same physics underpinned the design of the jet engines now entering production. Rolls-Royce's early jet prototypes, including the Derwent and Nina, used ducted airflow principles derived directly from the P-51's radiator studies. The line between propeller-driven aircraft and jet propulsion had begun to blur. For the men who had built it, the satisfaction was both technical and human. Edgar Schmood, North American's chief designer, understood that his team's strange little invention had become something far greater than a fix. It was proof that even in the chaos of war, precision, patience, and logic could triumph. Engineers who had once argued over duct angles and vent geometry were now seeing their work define the course of history. As Allied airfields filled with returning squadrons in those last weeks, mechanics looked over their machines and realized how far the Mustang had come. Gone were the leaks, the bursts, the emergency landings. The same aircraft that once limped home smoking from coolant loss now flew 6-hour missions without a single mechanical fault. The machine had reached perfection through necessity. The Mustang story, and the story of its weird cooling hack, was not just about a machine that didn't fail. It was about the idea that every system could be optimized, that the laws of physics could be turned into allies rather than obstacles. It was a victory not only of battle but of understanding. When the guns finally fell silent in May 1945, the world began to take stock of what it had built to win the most destructive war in history. Among the ruins and the wreckage, the North American P-51 Mustang stood apart, not just as a weapon, but as a symbol of how engineering precision had changed warfare forever. Its long-range escort missions had made daylight bombing possible. Its agility had redefined air combat, and its reliability had proven that performance and endurance could coexist. The story of its cooling system, the so-called weird modification that turned wasted heat into thrust, became a case study across the aviation world. Engineers from Britain, the United States, and even captured German specialists studied the Mustang's radiator duct design. At first, many couldn't believe the results. The idea that a liquid-cooled piston engine could gain net thrust from its cooling system sounded like fantasy. Yet wind tunnel tests at the Royal Aircraft Establishment at Farnborough confirmed it. At high speed, the Mustang's Meredith effect radiator produced a measurable forward force, effectively offsetting most of the drag it created. This meant that for every pound of fuel burned, a fraction of the resulting heat was turned directly into propulsion. It was an accidental hybrid between propeller and jet principles. A moment in time when two eras of aviation briefly overlapped. Decades later, aerospace historians would call it the last great piston engine miracle before the jet age. Pilots who had flown the Mustang never forgot what it felt like. They described the aircraft as smooth, almost effortless. Unlike earlier fighters, which struggled with overheating in climbs or dives, the P-51 seemed to thrive on exertion. It could run full throttle for minutes on end without damage, allowing pilots to chase, climb, or escape at will. One veteran later recalled that the only limitation was fuel, never temperature. After the war, the Mustang's lessons spread quickly. The U.S. Air Force and Rolls-Royce engineers adapted its cooling philosophy into early jet designs. The concept of ducted airflow as both cooling and propulsion became a cornerstone of turbojet development. Even modern ramjet and turbofan systems owe part of their lineage to the airflow studies conducted on the P-51's radiator tunnel. What had begun as a desperate wartime fix became one of the most influential pieces of aerothermal engineering in history. The aircraft itself served on for years. In Korea, modified Mustangs fought once again, strafing columns and escorting bombers. Their Merlin engines, still running cool and stable under extreme conditions, were a reminder of how well the system had been built. Civilian racers, decades later, pushed the same engines beyond their design limits. 80 inches of boost, 400 knots, and the cooling systems held. The innovation that had been born in war became a legacy of endurance. Behind every mission, every photograph of a gleaming Mustang idling on a dusty airstrip was the invisible triumph of thermal engineering. What made the aircraft nearly perfect was not luck or myth. It was a chain of deliberate choices, equations, airflow studies, and hours of trial and error by men who refused to accept compromise. Their understanding of how to move heat efficiently had turned a fragile machine into a global icon. In retrospect, the weird modification was less an oddity than a revelation. It showed that the smallest insight, that waste heat could become useful thrust, could alter the balance of a global war. Every bomber escorted safely home, every dogfight won at high altitude, every mission completed over Europe traced back to that principle. The final evaluations written in 1946 by the Air Technical Service Command summed it up simply. No other piston aircraft of the war maintained power so consistently over so great a range of speeds and altitudes. The data spoke for itself. Hundreds of thousands of flight hours, thousands of successful sorties, a system that never failed under combat conditions. By the time jet engines took over the skies, the engineers who had built the Mustang had already moved on to designing the next generation of fighters. Yet in the quiet of testing facilities and the pages of post-war reports, the legacy of that one cooling innovation lived on. It was proof that precision thinking, even under the pressures of war, could reshape technology for decades to come. The P-51's radiator wasn't glamorous, it wasn't visible from the cockpit, and it never made headlines like the Merlin engine or the 6.50 caliber guns. But it was the reason the aircraft could cross Europe, fight, and return home again and again. It was the hidden mechanism that turned a fast plane into an unbeatable one. If you enjoyed this video, don't forget to like, comment, and subscribe for more World War II stories.